So welcome everyone. This is CISSA's Foundations of Algorithms Revision workshop that we run every semester. You might have heard about us. We're the largest tech club in University of Melbourne, and we do a lot of revision workshops like this for FOA, FOC mainly. And we also do a lot of industry events. We are sponsored by a lot of awesome tech companies like Google, Microsoft, Amazon, Canva. But we also have sponsors from a lot of different fields, including consulting and trading. So yeah, if you're interested, so join CISSA and come along to. We have a lot of like tech talks from these companies, and they do recruiting events with us as well. Joining is free. In addition to industry things, we also do a lot of educational workshops. So there's a revision workshop. We also run a workshop on like React, data science with Python. Chris is going to run a workshop on Rust later in semester 2. And we also do like hackathons and like entrepreneurship panels, things like that. If you're interested, please join with this QR code. Again, it's free. And you can also find us on Facebook by searching CISSA. And if you're not in a CISSA discussion group yet, please join that page. It's sort of like a separate thing. It's more of like a student community forum thing. Yeah, like so that's sort of associated with CISSA, but you just kind of like use it to ask questions about subjects. Just ask for advice and like banter or whatever. So I recommend joining CISSA discussion group as well. All right, so that's my slides, and I'll hand over to Chris, who's.
Alrighty. Yeah, thanks, Andrew, for the introduction. So my name's Chris, and I will be presenting for the first like 45 minutes or so of this revision workshop. So what I've done is I've chosen a couple of like select topics from the course to go into a little bit more detail about. And so I'm going to do a presentation here together as a whole group, and then probably in the second half of the revision workshop, we're all going to split up into breakout rooms, slightly smaller group, and work with some past exam questions. And we've got a number of different demonstrators who will each be guiding you through that in the breakout rooms. Sorry, I just need to get the chat up. Okay, sweet. Yeah, so I've just written here like a bit of a shameless plug to my own GitHub, where I've put some of my lecture notes on up there. Some of the content I've taken from this is from these lecture notes, but I'll post the link in the chat. I think someone asked about that, but to be honest, they're not super complete. When I did the course, I had a little bit of assumed knowledge, so I didn't write like everything you need to know down. But in case you find that interesting, there's also some links to other people's notes that they've taken on GitHub, so that, yeah, you might like that. Onto the topics that I wanted to talk about. So the first thing was just a bit of an overview of some different sorting algorithms, and particularly like how to think about their time and space complexity. So I'm not going to be going through the entire like pseudocode, but more just an overview of how they work. And then looking at a little bit about like pointers and dynamic memory allocation, and then a little bit about linked lists and binary search trees, and then we'll go into more detail with that in the breakout rooms. So I guess going on to this section on sorting algorithms, this is like obviously an important part of the Foundations of Algorithms course because you end up using sorting all the time. And I guess what I've got here is much more general than just sorting algorithms, but we see it, I guess, first when you start looking at sorting. So we've got this notion of time complexity and space complexity. So it's important that while some algorithms might be, say, better with respect to their time complexity, they might actually be worse in respect to space complexity. So you have to consider like both of these as a trade-off sometimes. Time complexity we can define as essentially counting how many CPU instructions are being executed. And that's a very rough estimate, of course, because we don't know exactly how our C code is going to turn into actual code. And then you can do something like expressing that as an estimate in terms of big O notation. So in that case, you do something like if you've got some number of instructions that ends up being, say, like n minus 1 times n all on 2, that ends up being like a O(n squared) algorithm. And then the same thing for space complexity. Here we're sort of counting how much extra memory is required to run this algorithm. And something really important to remember is like stack space does count. So we'll see that example with Quicksort. Before I go into this, I just had a question for all of you. So I'm going to look at insertion sort, Quicksort, merge sort, and heap sort. I was told that perhaps merge sort and heap sort weren't covered this semester. If you could let me know either way whether you'd like me to go over those or not in the chat, or just unmute your mic, that would be fantastic. Yeah, okay. So yeah, heap sort and merge sort was covered. Yeah, okay, cool. Yeah, so I'll probably end up going over those because I think they're quite useful. I guess they're probably on the more complicated side because insertion sort makes a bit more sense. So I guess, yeah, just starting with insertion sort. Of course, we've got some list, like, I don't know, 1, 7, 3, 6, -2. And then we start with a single element list, 1, that's already sorted. And then we try to insert the next element into our like sorted list. So we insert 7 into that list, that's still sorted. We try to insert 3 into the correct position. And to do that, we have to swap 3 and 7 and so on. You probably get the idea there, 3, 7, and so on until we've got the entire list has been turned into sorted order. So here's like a bit of pseudocode here. You could translate that to C code if you want. I'm not going to go over that in great detail because we don't have too much time. But in terms of looking at the time complexity and space complexity of insertion sort, I guess we can start with the easier part, like space complexity. You can see here that from the pseudocode of this function, we've got like an input array that takes up space, of course, but we don't count that as space complexity. What we do care about is whether we're allocating like extra memory within this loop, whether we've got recursive calls or not. And so we don't. The only extra space we might need is like some small amount of stack space that's constant. So space complexity here is constant. So you can write big O of 1. Onto time complexity of insertion sort. So I guess the idea is for each item that we insert, we have to do n insertions, and for each item that we insert, we might, in the worst case, have to move that item sort of like n swaps going all the way from the back to the front. Say we're inserting something, or we're sorting a list that was in reverse sorted order, and so we'll have to sort of swap everything around. So in that case, you can see that we're doing like n loops over n loop iterations in this outer loop here. And then we're doing sort of max worst case n swaps for each item. So then that's where you get this intuition of, okay, the time complexity should be O(n squared). That's obviously a very sort of layman's terms way of thinking about these time complexities, but I think that's also like really important just to have that like off the top of your head understanding of like, okay, why is insertion sort slow? And when I say slow, I guess I should preface that by saying like in many cases, if you know that the size of your input array is going to be very small, insertion sort can be very useful. Any questions about what I've talked about so far? Otherwise, I will go and talk about Quicksort. Yeah, so I guess Quicksort here, like I've taken some example code out of Alistair's book. So you've probably seen this code before. Once again, I'm going to be talking more about like the intuition of the algorithm and then how we look at its time complexity. So I guess the idea of like Quicksort is if you've got some array, you want to, and say this array's got elements in it. I'll put 5 in there as well. The idea is that you want to partition everything in the array by some partition element. So say we choose the first element as the partition element, then you want to find, or sort of almost create 2 separate arrays out of this, where you have everything that is smaller than the partition, in this case just -4. Then you've got the partition, and then, or you've got the pivot element, and then you've got everything that is greater than it, so 5, 3, and 6. So you've almost got like 3 separate parts to this array now. And then you say, okay, I'm going to recursively call Quicksort on this lower section. I'm going to call Quicksort on this upper section. And then until you, like, you keep doing that until you get down to your base case. And then at the end result of all of that, like, you'll get a sorted array out of that. In terms of time complexity, something to note is, like, in the worst case, say we chose a partition, say we had this same technique of like choosing always the first partition, the first element as the pivot. That would be a very bad way of partitioning your input array, because, for example, if you had an already sorted array and you called Quicksort on it again, then each time your pivot would be right at the start. And then every time you call partition, you'll get nothing on the left, and then you'll get n-1 elements on the right. And so that turns what should be this, I guess, like divide and conquer algorithm into just a decrease and conquer algorithm. So that's sort of the worst case behavior that you get, which turns Quicksort's worst case into like this ON squared worst case. So if you implement Quicksort badly, or if you've got like really bad input to Quicksort, then it can be just as bad as insertion sort, I guess. Except you've got all this like additional complexity of implementing it. It's much harder to code an implementation of Quicksort. But then, yeah, of course, if we do use something like a randomly chosen pivot element, then and you have a good sort of way of generating random numbers for that, then we should get much better performance, because each time we call partition, we're hoping to get roughly sort of splitting the array into half. So then we really are sort of dividing and conquering. Something to note with Quicksort, just remember that Quicksort, because you need, like, you sort of need recursion to implement Quicksort. There's no clear, I guess we could call it like a tail call optimization that allows you to turn this into an iterative approach. And so each time you make a recursive call, you use a little bit of extra stack space just to store the like input arguments for Quicksort. So even though we're not creating like additional scratch space, like perhaps we will in merge sort, which you'll see later, Quicksort still does have this additional space complexity. It's important not to forget about that. Although I guess in the best and average case, like O log n space is usually pretty good, because you can have maybe an array of like 1 million items, and log base 2 of 1 million is quite small. So it's not that much space. Just going on now. So merge sort and quicksort. I've heard from a few people that merge sort and quicksort were covered, but like perhaps not into full detail. So I'll probably do the same here, talking about maybe the intuition about why they might be more efficient. But yeah, I won't sort of go over like how you would code an implementation yourself. Although if you are sort of aiming for top marks in the subject, that's something I would recommend, is just try and like implement all these algorithms yourself with it, without looking at any sort of resources. Like just throw away Alistair's book and then try and do it yourself. Yeah, so merge sort. The nice thing about merge sort, I guess, is we've got this guaranteed O n log n time complexity. And you can see that if I draw a sort of pictorial diagram. So imagine we've got this input array. I'm not even going to write elements in it. Oh, actually, maybe I could. We've got 7, 2, 6, 3, 5. We'll put a 1 in there as well. And then we split up the array into sort of roughly equal sections. So in this case, this, and then split it up further. And then I guess we could do this like next step of actually splitting it into just individual single element arrays. And then this is like our base case, because we know that an array of only one, sorry, I just zoomed in on my iPad for a sec. So we know an array of only one element is sorted. So that's like our base case. And then the idea is, of course, we've got this merge operation that will take two arrays, and it's going to take two arrays and then it's going to merge them together in this sorted order. So in the instance of here, we can get so 7 and 1. Those two arrays, we're going to take the element from the this array first, and then we're going to create an array like 1, 7. I probably should have given myself a little bit more space here on this slide because I'm drawing over other text. So yeah, that's an intuitive explanation of the algorithm. What I wanted to look at was sort of drawing out why we only have O n log n time complexity. So yeah, sorry. So I might just scroll up a little bit. Actually, I could even, yeah, okay. So the idea here is, so I've got an array here, split it up into smaller pieces. And so each time I do a merge operation, you have to sort of loop through each element of one of the arrays and decide which one to copy, and then copy it into a new array. So that merge operation is going to have a time complexity proportional to the size of the input. So actually, if I draw this the other way. So we've done the splitting. The splitting doesn't really take any operations to perform. It's just like, because you're not actually splitting up the array, you're just making recursive calls with smaller and smaller sub-slices of the array until you get to these single element arrays. And so then, yeah, so then building it back up, you've got like these merge operations. So two arrays of length 1 get merged into an array of length 2. Arrays of length 1 get merged into an array of length 2, and then two arrays of length 2 gets merged into an array of length 4. The point I'm trying to say here is that the number of layers that we have to perform here to get back to our complete array, there's log n layers. And then for each layer on this sort of axis, here we're going to have to, sorry, on this layer, we're going to have to perform 2 merge operations of 2 sort of elements each. And then on this layer, we're going to have to perform one merge operation of 4 elements each. And the idea here, I guess, is that, so this is for an array of length 4. But on each of these layers, you're going to have to perform roughly sort of like n copies to do all of your merge operations. So if you multiply both of these together, what you end up getting is like the n log n time complexity that we expect from merge sort. So that's like how I think about merge sort on a conceptual level. And then of course, what we've got down here is that we do need, you can see here in the pseudocode, although I haven't really written this all out. When you're merging, you can't just merge in place. You need this extra array to copy results into. So that's why you get this extra space requirements. And that's one sort of undesirable property of merge sort. And that's, I guess, why heap sort, at least conceptually, is quite a cool idea. In practice, of course, we know that heap sort ends up being not super efficient in terms of its implementation on, like, say, the modern CPUs. But heap sort does end up getting used. For example, they've probably mentioned in lectures, heap sort will get used in, for example, the Linux kernel, where it's really, really important that there's only sort of a constant space requirement when you're sorting. I'm just checking how I'm going for time. Okay, going all right. So yeah, I'll talk about heap sort quickly. Yeah, so the actual pseudocode explanation for heap sort is quite simple. We've got this first step, heapify, where we build up a heap from this array. And I guess importantly, you can think of a heap as like a tree that has the heap property. So in this case, this would be a min heap. So each parent element has to be less than either of its child elements. So you can think of a heap as a tree, but the smart thing that they've done here is when you heapify, we don't actually need to construct a tree like we don't, like sort of a physical tree. We don't need to like allocate a bunch of memory and create all these pointers like you would with, say, a binary search tree. Instead, you can construct this tree in place. So, for example, this tree that I've drawn over here, which happens to be a heap because it satisfies the heap property, you can also write it out as hold on, no, that's not right. So the idea here is that this wouldn't work because we've got unfilled elements here on the left. So we'd need some other items here. So like, I don't know, 11 and 13. And then what we can do is we can write 11, 13, 9, 10. And then there should be this sort of one-to-one mapping between the array here and the sort of visualization of it as a tree. So that's kind of cool. And then, like, what do we do with that? So we've got this heapify function, which will swap all these elements around such that the array now can be considered a heap. So it satisfies this heap property. And then all we do is we keep calling eject on each element. And so what eject will do is take the first element or the smallest element in the heap and sort of take it out of the heap and then sort of reorganize everything so it's a heap again. And if we do that, then we've built up this heap, and then I guess it's sort of like insertion sort, except more efficient, because each time you call inject, that's like an O log n insert into the start of the array. Yeah, I think heap sort, I'm not sure how much detail they went into it this semester, but I think it's definitely useful to have this sort of conceptual understanding, but it's definitely one of the like trickier parts of the course probably. If you go on to do design of algorithms next semester, you go into more detail with this. But yeah, so the general idea here is that the heapify process, so I've written it down more here, I won't talk about it entirely, but heapify, the whole process you can do in ON time complexity. And ejecting a single element you can do in O log n, which is fantastic. But in order to sort this array, you have to call eject n times. So once again, similar to merge sort where we had this, okay, n operations here and then like log n layers. Similarly, for heap sort, we've got sort of a log n operation that you have to perform n times. So the overall time complexity is n log n. I guess you can also remember that just by there's a theoretical lower bound on how efficient you can make sorting. So comparison-based sorting algorithms, like you physically cannot make one that is more efficient than n log n. So that's something else to consider. Anyway, yeah, so that's what I had on sorting algorithms, just like a brief overview and a discussion of like time complexities in particular, and also space complexity. And I guess, so on space complexity, the important thing here is that you can have iterative implementations of heapify and eject. So you don't need this recursion, you don't need the extra stack space, so you can get O1 space complexity. Before I move on, did anyone have any questions? Actually, I think I got a message. Oh, would I be able to share the file that I have on my screen? I definitely will. If it's okay, I might put it together afterwards and I'll create a PDF out of it. And then that might be easier to read then. But yeah, definitely I'll put that on the Facebook group. Yeah. So yeah, so the next thing I want to talk about was dynamic memory allocation and sort of everything that goes along with that. So pointers and structs and all that. I think this is like, hopefully you have a decent understanding of how this works at this stage in the semester. I think it's very much underpins like most of what you can end up accomplishing with C and with just like these low-level languages in general. But yeah, I was going to talk a little bit about this. So I guess firstly, why would you want to use dynamic memory allocation? It's so much easier to just create variables on the stack, right? Because you don't have to worry about calling free, and you don't have to use malloc either. And yeah, there's just like less effort overall, right? Well, I think, yes, that is true. And that's why when you can, definitely store variables on the stack. But when you must, and there's a few instances where you just can't accomplish what you want to accomplish with the stack, then you'll need to resort to dynamic memory allocation. And so a few instances of that would be like, okay, maybe someone tells you that, oh, you need to read input from a file, and the first element in the file, the first line of the file will tell you like how many elements you have to read, and then the next n lines will be the actual data to read. So in that instance, you don't know ahead of time the maximum size of your data, so you need to use dynamic memory allocation. Also super useful for implementing like linked lists and BSTs. That comes up in the practice exam we're going to look at. So if I get a bit of time, I'll talk about that briefly before we move into breakout rooms. And yeah, I guess also, yeah, there's instances where you might want to create an object inside of a function and then pass it back out to the caller. And you don't want that object to get automatically sort of deallocated when you exit that function, and you want to have manual control over like when you're done. Because I guess the idea of a stack is you enter the function, you can put things on the stack, but then as soon as you leave that function, that memory, well, it doesn't go away, actually. It could get reused for different function calls. It'll get mangled into all sorts of random data. So if you end up using that memory, you'll get some sort of undefined behavior. But yeah, I love what's going on in the chat as well. So yeah, do we prefer to use stack, but if we can't, then use malloc? I'd say that's probably the exact idea. The stack is easier to use, it's faster. When you can use it, definitely make use of it. But then malloc is like I guess it's the more powerful tool that also comes with great responsibility. And yeah, so stack enables you to do less cleanup. Does malloc not use the stack? So I guess in a way it does. So when you call malloc, you're entering another function. So say this is your stack and you've got a bunch of different function calls, like I don't know, if something, and if you call malloc, you're entering another function, so that will push sort of more data onto the stack. So this is like when you call malloc. In that sense, it uses the stack, but the actual data that is the pointer that's returned from malloc is like off here over in heap land. And you'll get some pointer, like you get a pointer, say you store it somewhere local to your function, and then that pointer will sort of point off to this region of memory. So I guess you could think of malloc allows you to, it's still using the stack because the pointers that you store will sort of originate from the stack perhaps, but then it allows you to make this bridge into all this other memory that's like over here that you wouldn't be able to use otherwise, memory that's on the heap. And so you can have like a pointer into something on the heap, and then say this is the linked list, then you can have like, you know, something else on the heap, and it just keeps going. And malloc is like the tool that allows you to make that connection. Yeah, hopefully that sort of explains a couple of those ideas. Yeah, so there's sort of four main functions. These two, I would say, are must know. The next two are more specialized. So malloc and free, the idea would be that every time you call malloc, you need to make sure that there's a corresponding point in your program where you're going to call free on that same block of memory. Realloc can sort of happen in between. You could malloc once, realloc that same memory a number of times, but then you'll still need to call free at the end of it. And calloc is really just when you want to allocate memory and then you want to clear it and like immediately. So that's just an optimization. You could call malloc, and then there's also this function like memset that will, yeah, so memset will, you can set everything to 0 with that function. So you could call like malloc and then memset every time, but if you're going to do that, then it might be easier to use calloc. It probably will be faster as well. This is a really interesting question. So if I miss free somewhere, will you get any errors that prevent your code from compiling? So no, you won't. And yeah, so Nathaniel has explained that really well. So C as a language doesn't give you enough sort of abstraction to ensure that when you malloc, it sort of can track that pointer and know that you're going to free it. If you're at all interested in that, then please come to my Intro to Rust workshop next semester, because Rust is a language that attempts to solve that problem. Or you could go back to Python, because Python also solves it in a different way. But it's considerably less fun, I guess. And if you don't plan on using realloc, what's the point of using malloc? Yeah, actually, yeah, thanks Nathaniel for answering these. So I think it's sort of like, there's many reasons why you just use malloc and free by themselves. All realloc does is, if you have an existing memory allocation and you would like to resize it in place, so it's got some data and you'd like to add more data to it. Say you've got like a vector and you've added 10 elements and you want to add an 11th, but you don't have enough space, you can realloc and it will give you more space to grow. That's also sort of an optimization. You could always use malloc, create a completely separate, so you could create a completely separate piece of memory. You could like copy each of these elements over, and then you could free the old block of memory, and then that would essentially be the same as realloc. Realloc just will do it probably more efficiently than that. Yeah, that's the idea there. Oh, okay. I heard somewhere that recommends realloc is used multiplicatively. Can you explain that? I'm not quite sure what's meant by multiplicatively, but I think, could it be, so if you've got an array, so you've got an array of 10 items, or let's say your array starts with the size of 4, because it's nice because it's a power of 2. Yeah, so the idea, I think people have it very well in the chat already. So yeah, the idea is, if you're going to call realloc, if you just add on a bit of extra memory every time, then if your memory use is going to eventually grow a lot, say you start off with an array of size 2, and you're eventually going to want to add 1,000 elements in there, and each time you just add 2, then you're going to have to do like 500 reallocs. Whereas if every time you want more space, you double the amount of space in your buffer, so you go from like 2 to 4 to 8 to 16 and so on, then you're only going to have to do like sort of like a logarithmic amount, so like roughly, I don't know, like log 1,000 reallocation. So like it'll be something like 10 or something. So in that sense, it's usually doubling the amount of memory that you have in a buffer when you need to realloc is like a good idea. There might be exact values for different scenarios that are better, but my rule of thumb is like, I don't know, start with a size of 2 and then just sort of keep multiplying by 2, because it's easy for computers when things are always powers of 2. Yeah, so I think I've got about 2 minutes before we move into breakout rooms. I've got 2 different things I could talk about in that time. I could talk a little bit about pointers, but we've sort of already mentioned that a little bit. Or I could talk about binary search trees, because I think that comes up in the practice exam. Does anyone have a preference for that? Nope. Okay. Maybe what I might do is I'll skip this section. You can have a read of that in your own time when I post the slides. The general idea is just like, pointers are dangerous. Please be careful when you're using them. And this is just an example of where you might want to use malloc or realloc. So yeah, so now what I can talk about is, I guess, yeah, linked lists would be the simpler example, but then binary search trees are perhaps a bit more fun. So yeah, the idea of binary search tree is you've got a root node here, and each node in the tree is going to have so it's a data element, and say this could be an integer, so put like 7 in there. And the idea with binary so binary aspect of binary search trees is that each element is going to have two children. So you're going to start off with this root element, and then when you want to add something, you've got like two pointers which point to somewhere else in memory. So each one of these sort of blocks of memory is usually going to be like individually malloced. You can optimize that if you want, but yeah, that's the general idea. And so then the other part, so it's not just any binary tree. In order to be able to search this tree efficiently, you want to have this property that everything on this like sort of left side is going to be smaller than the root node, and then everything on the right side is going to be larger. So this would be a valid, yeah, this would be sort of like a valid binary search tree. But if, say, I had the number, if this was larger, if it was 15 or something, then that would not make much sense. I think perhaps I've confused people a little bit by how I've drawn this tree. So perhaps an easier way of drawing it would be to have the left pointer coming out of the left-hand side. But essentially, what I'm trying to convey here is just that you've got each node in a tree is a struct, and you've got sort of the data part of the struct, and then you've got two pointers in the struct. And it doesn't really matter in which order those elements of the struct are stored. That can just be like something that is like a cache optimization, for example. Yeah, so if there's two identical nodes, so the idea is, I think you, by convention, can just choose that if like all sort of equal elements will go to one side. So it could be that the left side is everything that's strictly less than, and then everything that is greater than or equal goes onto the right-hand side. So then you can still deal with duplicates like that. And yes, the idea with searching binary search tree, I'll do a slightly more compact example so I can do a bigger example, would be that you've got, so an element, let's do letters just for a bit of fun. Element G goes off to an element B, and then A, D. Let's say it's like this. And say I want to see if I want to search for the element N. So is N greater than or equal to G? Yes, it is. So I go down here. Is N greater than or equal to Z? No, it isn't. So I go to the left. Is N greater than or equal to M? Yes, it is. But there's no leaf node here. So that blows up. And then we know that N is not in the tree. I should have mentioned as well, each time we visit one of these nodes, we first check, okay, is N equal to G, or is N equal to Z, or is N equal to M? And if we find it here, then we know that it's in the tree. Yeah, so I think that's about time for everything that I wanted to cover at the moment. I think what we're going to do now is go, oh yeah, I've got a couple of questions. But after I answer those questions, we'll go into breakout rooms and then go over some past exam questions, I think, because that's probably a good way to find out what's involved. Yeah, so yeah, thanks, Desmond. So yeah, like a binary search tree, it's the main property, I guess, is that instead of like a normal array, if you want to search for something, you'll need to search you'll need a sort of ON time complexity to be able to search, like do a linear search through an array. But if, say, you store it in a binary search tree, or even if you store it in like a sorted array, which essentially becomes a similar structure, then you can get like O log n time complexity for search. And it's easy to see n and log n and think, oh, they're not all that different. But remember the example before, if n equals like 1,000,000, then log n is way, way smaller. It's, I don't know the exact amount, but yeah. It's like 20 or something. Yeah, and I think also the thing to say would be, if you are interested in, like, binary search trees is just like one instance of trees. It can end up being quite, like, you can sort of extend this concept into other things, like in the next subject, design of algorithms, you learn about like AVL trees and red-black trees. And that's sort of interesting. Also in game development, if you've ever looked at like different game engines, there's things called like quad trees and oct trees, which are used for doing collision detection and like game physics. Like I think if you look in like the Quake engine or something, like, which is quite interesting. Runtime of creating a BST. So if you're sort of constructing it by mallocing each element, then yeah, I think n log n seems to make sense, because for every element you want to create, you would need to potentially do an O log n insert. So you might need to sort of look down the tree up to a maximum depth of around like log n. And it's important to note that this is all average case, because the worst case of binary search tree is if you insert A and then you insert B and then you insert C and then you insert D, and then you have what people have referred to as a stick, and then everything decays to like the height of your tree here becomes n. Then everything decays to like O n instead of O log n. All right. I think that's enough for me so far. There's really awesome questions that have come up, and thanks for everyone in the chat also like contributing and answering those. I think it's good to get the discussion going. But yeah, Andrew, do you think we should open up breakout rooms now?
Yeah, I think that's a good idea. I'm going to open up, I can't remember, 5 or 6 rooms.
Yep, that should be recording. Can everyone see my screen at the moment? Yep, all good then. I'm going to basically explain a lot on, oh wait, you can, yeah, I'm assuming you can hear me. I'm gonna explain a lot on mostly linked lists and tree questions in the sample exam. So there's this sample exam that CISSA is giving us tutors, but we can't give it to you guys for reasons unbeknown to me. But if you want to look for this sample exam exactly, I think you'd have to look at Studoku or some other aggregator site. But let's begin. I'm recorded, right? Yeah. Yep, I am. So I'm going to be discussing question 4 and question 5. Question 4 is a question on linked lists. I'm assuming you guys are familiar with Alistair's linked list example code. And question 5 is on binary search trees. But this is, I think, very, very similar. No, actually, it should be the same as Alistair's example code for binary search trees. Oh, wait, my screen is not the question. Oh, is it? Oh, no, wait, let me skip that circuit. Oh, I'm on the wrong desktop. My bad. Should be able to see that now. Yeah? Yep. Yeah, this is pretty standard Alistair stuff. You can literally go to his website, get this, and like use it on your own, but should be fine afterwards. So question 4 is basically, given this entire definition of list things, we have to write a function called insert sorted, which inserts something new to a list, but insert it again. I'm pretty sure you guys have seen the insert at head or insert at tail that just inserts it at head or the tail. But this time we have to implement something that inserted in order. So this question is honestly more tedious than anything else because you have to think through a lot before you start. But it's useful to think of like the steps of the question in English first before starting to do any code, because trust me, I've tried doing this without thinking first, and it took me like 3 or 4 days to get it right. Don't do that. So first we want to find like the right place for insertion of the new item within the existing list. Then after we find the right place, we want to create a new node, and then we link that new node to the proper position inside the list. And if needed, we update the list variable accordingly. Like let's say the new thing is a head, then we update the head to be it, or if it's a foot, we update the foot to be it. So this is like the steps in English. You've read it already. And converted to code, it's basically this chunky boy that we have to work through slowly. So I'll explain the code for a bit. After explaining the code, I'll take you through a visual example thing where we actually insert things into a list. So first, I'm pretty sure you've heard of this from Alistair. You have to do some assertions to make sure that the list isn't empty and all that. And you declare some helper variables to help you throughout the entire processing that's going to happen below. So the very first thing that we're going to do before anything else that's like pretty much mandatory is we have to find where to insert the new item into the existing list. So this block of code basically starts from the beginning, compares the value of the new node to be created later on with the existing, like the very first node in the list. If it's less than that value, it's not in the right place because we want it to be like in order, so something that is bigger should come after. So if it's less than, and like the current thing isn't null, so we haven't reached the end of the list yet, we just keep on stepping to the next node in the list. And this while loop's gonna run as long as it's on the end of the list and the current data is still less than the value of the new value, sorry. Then after those two things are broken, so either we reach the end of the list or the data to be inserted is now bigger than the current data in the list, it'll stop. And at that point, we'll have reached the point where we want to be in the list. Does anyone have any questions so far? Or if it's preferable that you like just answer to me in voice, because looking at chat is a bit annoying, but if you want to do it in chat, go for it. I'll make sure that I check into chat periodically. I'm assuming that there's no questions, so I'll continue on. The second thing that we're going to do is we allocate memory for a new node with the new data. So that's pretty straightforward. You just call malloc. Make sure the malloc works. That's very important. So make sure malloc actually returns something. And then we set the new data into the value that we want to insert into the list. And then after that, it's the link the new node to the existing nodes and update the list accordingly. This is a bit confusing, if you ask me, because there's like two separate if statements that run after each other. But I'll take you through it slowly, and hopefully you understand what's going on. So because the current node is larger than the next node, we're gonna link the new node's next pointer to the current node, because new comes before the current node. That's like the very first thing you do. That's to make sure that the new node has like nodes that are connecting after the new node, so it doesn't just lead nowhere. Then after that, we check if the current node is like the last node or not, because if it's the last item in the list and the new node comes after the current node, hold up, let me. Yeah, that sounds about right. And then we set the new node to like the list's footnote, because now it's the last node. And then if there is a previous node, we take that previous node and then we link its next pointer to the current node, which is done by like this pointer assignment. But otherwise, if there's no previous node, then it implies that the node is basically the head of the list. So we have to update the head of the list to the new node. Does everyone understand it so far? Or if you guys are like reacting, forgive me because I don't know how to check participants. Yeah, okay. Any questions on this like list question thing? The next like list questions are gonna be on sorting complexity. So if you take this entire like algorithm as a sorting algorithm, what would its complexity be? But this is like the basic implementation of an insert in order into a list. Oh, if I'm going too fast, do tell me because I tend to speak very quickly. Assert basically checks for some value of if it's not like something. So if the assert fails, your program just crashes. It doesn't really crash. C stops its execution. In this case, this assert is kind of what you call that, implicit. But this assert, when asserting new, is exactly the same as this assert. So it's checking that new isn't null, because when malloc fails to allocate memory for you, it returns a null. The thing is, this assert has to happen because if this, let's say, returns a null, this next line is going to throw an error because you can't access the member of a null pointer. But like this entire block of code is basically this, but in C. So if you can work through it accordingly and like given, I mean, this should be enough time in exam to do this. It should be fine. But it is highly recommended that you first write it in English what you're gonna do, and then move on to coding it to C, because if you don't, you can get caught in like some really tricky edge situations. Like there was a project I did this semester where I was implementing this exact function in one of my linked list functions, but this was an equals. So it threw everything off. And it took me like 3 or 4 days to finally realize that it shouldn't be less than equals, but it should be less than. But yeah. In terms of code complexity, I think this is pretty much as complex as it will get in regards to linked list code, because normally you're just asked to like, let's say, traverse through the linked list and do something with the data, or count the length of the linked list or something like that. Do take that with a grain of salt because Alastair didn't teach me when I was taking foundations of algorithms, so our question stuff should be a bit different. Any other questions before I move into like the pictorial representation of the algorithm? Binary tree. Usually there's like one linked list question and one binary tree question. That's like the ideal case. Though I'm not sure where he'll like make it difficult in, because Alastair has these questions called like, I'm not sure if they still exist now, but we called them bastard questions in our day. So it's like a question on a topic, but he jacks up the difficulty so high that it becomes an H1 filter. At least last semester when I was taking FOA, not last semester, last 2 semesters. Yeah. The hard question was the binary tree question. And I got like caught up in it. So I didn't end up getting a really high grade. But yeah, that's just luck, I guess. But like I think if you can do this code on your own, like, you know, write the code on paper, make sure it works when you test it and with GCC and stuff, you should be fine with like most of the linked list questions. Oh wait, you're not having Alistair for a semester. I'm not sure if that's a good thing or a bad thing, but just be prepared, I guess. Because another question that can appear for linked list is, if you've noticed, we're doing this iteratively. So we're like taking one node, we're stepping to the next node, and we're stepping to the next node. Another question style for a linked list is doing it recursively, because technically speaking, a linked list is a recursive data structure. But even if that's the case, it should be pretty intuitive if you've learned how to create recursive functions. Oh, Chen Chong, he was the same person that teach me last time. He gave me a hard 3 question, not appreciated, but yeah, that's just how it is. But yeah, you can get this question iterative. You can get an iterative question on a linked list on which you have to decompose it to, you know, the edge case where like the recursion should stop and the rest is just working on a linked list that is one node less than the current linked list. If we have enough time, I'll try look up a question like that and I'll walk you through the solution. But for now, I'll move on to the pictorial representation of the algorithm. So let's say we want to insert 3 items in order into the current list, which is at the moment only contains 2 and 4. If we insert 1, according to this algorithm, we find the right place for the insertion within the list. But since 1 is already, say, it's already where it belongs, which is before 2 and before 4, it just gets inserted. And this entire block of code basically does the creation of this link. And then after, let's say, we inserted to 1 to 4, and we want to insert it to 3. We want to insert 3 into the existing 1 to 4 list. So we do the same thing again. We look at the first element. We check if it's like, if 3 is in the right place there. It's not, because 3 is less than 1, and we should insert it after 1. So we're gonna step forwards. But after we step forwards, we also realize that it is not in the right place yet. So we step forward again, which is what this while loop does. After the next step forward, we figure that 3 is already in its rightful place because it is greater than 3 and less than 4. So we should insert it there. And once again, this code block over here does the linking between the previous node and the next node. That's inserting a node that belongs between 2 other nodes. Next, we're gonna insert a node that's basically belongs at the end of the list. So we take the 5 node, we compare it to the 1 node, we realize that nope, it's not supposed to be here, so we step through. But it's not supposed to be here either because 5 is still greater than 2, so we step through again, and so on until we reach the end of the list. At the end of the list, the code basically runs into like something like a roadblock because it's reached the end of the list. So it just stops iterating because you can't go any further. And then after we check that 5 is in its rightful place because it didn't pass any of the tests beforehand, we just insert it in the list. Once again, this block of code does the list updating and like node linking, but we make sure to update the tail of the list, the foot of the list. Oh yeah, that's what Alistair uses. The foot of the list to the new node because it got inserted in the very last place in the list. And then after all that insertions, we have basically a sorted list. And I'm also going to preface that this is what Alistair gives, I think, or whoever publishes this sample exams as an answer, but there's like different ways that you can do this. So don't take this piece of code as like the be-all end-all insert and order list code. I'll show you like what I did last semester in one of my subjects later on if we have time, but it's very similar to this, just that it's a bit longer to make it a bit more readable compared to this, because this gets kind of confusing if you follow through it, unless you're like really, really careful. So keep in mind like how the 5 insertion behaves, because that's going to be pretty important in the next part of the question. Does anyone have any questions so far? regarding like the visual representation of an insert and order listing? No? Then I'll move on. So the next part of the question basically like takes us to consider the previous algorithm, which is the insert and order, as a sorting algorithm. So if we were to use it to sort, how would it perform? So the first question asks, what is the best case input for the algorithm above? And if you've noticed, when we insert 1, because it's like the smallest element in the list, we don't have to move forwards to like insert it. We just insert it in the head. So we don't have to like touch the rest of the list at all. The best case input is when that happens basically all the time. So whenever you want to insert an item, it just checks the first item of, in the list and says that, oh, the next item is going to be smaller anyways. So let's just insert it at the head. Because when you do that, you don't have to look through the list. So you only have to loop through your insertion array once. Because whenever you land on something to be inserted, it's always guaranteed to be inserted in the very first position in the list. So keeping that in mind, the best case input would be a reverse sorted list. Because if you, let's say you're building this list from like an empty list, and you had a list that you want to sort. Let's say the list was 3, 2, and 1. The first insertion 3 is just going to be inserted in the head because the list has no items yet. That's like relatively straightforward. But when you want to insert the next item, which is 2, it checks if 2 is less than 3, and it is less than 3, and it belongs before 3. So it'll just insert 2 at the head. And then when you want to insert 1 into the existing 2, 3 list, it's just also going to be inserted into the head. So there's no need for us to traverse the list to find the right position to insert, because it's always the first position. Because we only have to like loop through the insertion list once, and we don't have to like loop through the existing list to be inserted to at all, the time complexity is O(n), because if the list to be inserted is like length n, we just have to look at the first item, insert it, look at the first item, insert it, look at the third item, insert it to the head. So it's just going to the list once. So it's O(n). But if we were to flip the question on its head and we ask ourselves, what is the worst case input for the algorithm? The worst case input would be something that behaves similarly to 5, where you have to check from the very beginning if it belongs there or not, and then it keeps on failing until it reaches the very end of the list. Because if you've noticed, 5 is the largest element. So we have to compare it with every single element in the list before finally figuring out that 5 is the largest element, so it should belong in the very last. So we insert it at the last. So the worst case input, keeping this in mind, would be a sorted data set. Because let's say you want to insert a data set 1, 2, 3, 4 into a linked list, and you build it from scratch once again because we're using the linked listing to sort. When you insert 1, it's straightforward. You just insert it at the head because the list is empty. When you want to insert 2, you first compare if 2 is less than 1 or not. You find that 2 is not less than 1, so you put it like to the right side of 1. And then now you have a sorted list which is 1, 2, and you have 3, 4 remaining to insert. When you want to insert 3, you do the same thing again. You compare if 3 is less than 1. 3 is indeed less than 1, so you go to the next position. You compare if 3 is less than 2. And it is not less than 2. So you go to the next position again until you finally figure out that 3 is bigger than everything in the existing list. So you insert the tail of the list. The same applies to 4, but what I'm trying to say is, if you insert in sorted order, because the next item you insert will always be the biggest item in the list that you're inserting to, it's forced to do comparisons with every single item in the list before it can finally like insert the item into the list. So because you have to look through you have to look through the list once for every single item you want to insert, the complexity becomes O(n) squared. Because you're basically looking through the entire list n times, since you have to look through the entire list once for every single thing you want to insert. This isn't a very good sorting algorithm answering this question, because its worst case complexity is O(n) squared, and that's really not ideal when you want to sort things quickly. And it doesn't handle random data sets well either, because if it's random, you still have to look through the list. You still have to look through at least half the list most of the time. So the average case complexity is also O(n) squared, because you have to look through n/2 list items n times, which is n squared over n, but it still ends up being O(n) squared anyways. And what makes it even worse is that this consumes linear space. So you need to allocate an entirely new list to sort an existing list. It's not done in place. So the space complexity is O(n), because you have this original array of things you want to sort, and then you have to create this entire list, which will be sorted eventually, but you have to create n list items to sort n items from the array. So it becomes O(n). And this is very not ideal, because come on, you have O(n) squared as time complexity, and now you need O(n) space complexity. Plus, if you even look at bubble sort, I think everyone agrees that bubble sort isn't a very optimal sorting algorithm due to its O(n) squared time complexity. But at least bubble sort does it in place, so it doesn't take any extra space, and its space complexity is O(1). Or better yet, you can just take the array, use Quicksort on it, get it sorted, and it's O(n) log n, no extra space. So this list insert thing that we had to implement in the first part of the question is not a good sorting algorithm, because it has a time complexity of O(n) squared, it has a space complexity of O(n), and it's gonna take a while to sort large data sets using this method, and lots of memory too because of the O(n) space complexity. Does anyone have any questions about that? Or I don't know, any questions in general? Because we can take a break a bit before we move on to the binary tree question. No. Okay. Then I'll move on to the binary tree question. This question is, compared to the list question that we just did, basically more straightforward. So this is not the hardest question that a binary tree can be, basically. There can be harder questions. But the part A of the question is basically draw a binary search tree if you were to insert this list of drinks into a binary search tree. And that should be pretty straightforward. I'm gonna assume that you all can at least do that. So when you take gin and then you take bourbon, which is less than gin because B comes before G, and you insert to the left, and you take beer and then you keep on going down the tree until you insert every single item in this list. The more, let's say, complex part of the question would be part B, where we have to make a function to calculate the tree size of a given tree. The tree size is basically the number of elements stored in the tree. And if the tree is empty, we return 0, and we can write more than one function. That's a pretty massive hint, because we're going to need to write more than one function. So once again, before you do any coding, write what you want to do in English for a sanity check to make sure you know what you're doing. So basically, we're gonna calculate the size of the tree, because that's literally the only thing that we're asked to do. But this in itself is going to recurse on itself, as you'll see later on. Because to calculate the size of the current tree, you need to calculate the size of its left subtree and its right subtree. And then after you calculate the size of both the left and right subtrees, you add them together and add 1 because you're also counting the current root node. This recurses because if you've noticed, this is an entire tree. If you take the left subtree of gin, which is bourbon, beer, coffee, it's also a tree. So you keep on recursing down the tree, calculating the size of the subtrees until you hit a dead end, which is basically when like the root has no children, so it's a leaf. So you'll see the recursive nature like in the function that's going to be implemented, which is this one. This is the function that does like most of the heavy lifting. The other function down below just provides a nice interface to the user using your recursive function. But basically the recursive tree size calculation takes a node and it checks. If the node is like null at the moment, that means you've reached a dead end. You're trying to calculate this. You're trying to calculate the size of an empty subtree. So when the tree is like, when the subtree is empty, there's no nodes in it, so you just return 0. That's the base case. What happens when you hit the leaf nodes of the tree. If it's not the base case, or in other words, if there is still a left subtree and a right subtree with nodes, you basically recursively call this function on the left subtree. You call this function again on the right subtree. Then you add 1 to take into account that you're counting the current root node. And this recursive call basically expands until it hits this case. When it reaches the leaf node of like a tree. Then it stops, then it closes, then it goes back up, and then it keeps on returning all this until it finally returns to the primary function call where you call it at the root of the tree. But a tip for doing like recursive things, it doesn't have to be trees, it can be lists too, is that you need to determine what the base case will be. And then everything that is not the base case, you have to like basically recurse on the function itself. And does anyone have any questions regarding the code? Because there's going to be a really, really short visualization, like taking you through the algorithm, but that should be really, really straightforward and easy to do. Nope, no. Okay, I'm going to assume there's none. So basically, we're going to call tree size at gin. And then because it's recursive, gin is going to call tree size on bourbon and vodka. And then vodka, bourbon, and vodka is also going to call tree size on its children until it reaches basically a leaf node. Because when it reaches beer, it can no longer call the tree size function on its left subtree or right subtree because there are no left or right subtrees. And then when that happens, it just returns a value of 0. If you've seen here, the size of the left subtree is 0, the size of the right subtree is 0. So the size of the tree that contains beer as the node is 1. And then this 1 gets returned to bourbon. Gets returned to when bourbon called the recursive tree size function. So bourbon knows that the left subtree is of length 1, and after a similar process, coffee will return a tree length of 1, and then it will return to bourbon. So bourbon adds the left tree size, which is beer, adds the right tree size, which is coffee, and adds 1 to itself because it in itself is an element. And then that returns the value to the call that gin made regarding bourbon. And that basically is the same with how milk, whiskey, wine, tea, juice, water propagates to the point that it keeps on going up, and then it finally returns that a vodka is a tree of depth 7 because there's like 7 elements in the tree with vodka as a root, if you see here. And then at long last, after all that recursive calls has ended, it returns the value of 7 to gin, and then gin can finally calculate the size of its left subtree and its right subtree. the left subtree bourbon is depth 3, the right subtree vodka is depth 7. So the total tree size is 11. And calling it tree depth isn't accurate because depth is just like how deep the tree goes. I should have called it size instead because we're calculating the number of elements in a given tree. But for a tree question, I'm not sure if this is like the hardest you can get it, but what I got last 2 semesters when Zhenjiang taught me was it's very, very similar to this actually. I was just caught off guard and I didn't study enough on trees, so that didn't end very well, but yeah. But you should be able to do fine with recursive structures like trees and lists if you're proficient enough in breaking down what the base case is and what the non-base case is for recursive structures. Like in this case, the base case is when you reach a subtree with of like height 0 because there's no nodes in the subtree. Then the base case is it should return a 0 because a subtree with no nodes is of size 0. And then the non-base case is basically everything else that is not the base case. If the tree is a stick, this will still work because if the tree is a stick, like imagine that this bourbon coffee juice tea milk thing doesn't exist, so it just goes gin, vodka, water. It's going to try call tree size on the left, but it's not going to find anything. There's no subtrees because we've imagined that bourbon is empty. So it'll just return 0 and it'll go to vodka and like call its stuff until it reaches the very end of the stick and it's going to return up again. So it's going to work very, very similarly. If the tree is a stick, checking a function. Oh, so wait. If I understood your question correctly, you want to write a function to check if the tree is a stick or not, is it? Okay. To check if a tree is a stick or not, it's pretty straightforward. A stick is like basically a linked list, right? So you keep on checking if you can go to one direction until you reach null, and that's the size of your entire tree, then it's a stick. But you need some auxiliary function to calculate the size of the tree beforehand. Or you need to at least know how many elements are in the tree. So you count the number of recursive calls. If the number of recursive calls exactly matches if the number of recursive calls in one direction, so only to the right or only to the left, exactly matches the number of elements in your tree, then you can like confirm that that tree is indeed a stick. Or like in simpler terms, you basically make sure that from the beginning of the tree, if you keep on going right, it keeps on working until you hit the end of the tree. And when you hit the end of the tree, you realize that you've already read everything in the tree. I'd admit that that's going to be a bit hard to implement in an exam because it requires more than 2 functions at least. But if you get the idea, you should be fine. You return 0 for base case because when you hit a tree node that is like null, it doesn't exactly have any members. So like the length of its subtree is 0 because it has no subtrees. Like if you take beer, there's no subtree on the left and on the right. So returning 1 isn't exactly right because when you return 1, it implies that there is an element in the left subtree and there's an element in the right subtree. Any other questions? If not, I can move on to the last question. This is more of a code comprehension question than everything else. Yeah, if it's a leaf, there's no left subtree or no right subtree. Like if you imagine using this code, if you reach beer and then you call this function rect_resize left on beer, like beer doesn't have a left. Left is null. So it should return 0 because if you return 1, you're gonna add 1 unnecessarily. But yeah, one can be counted a recursive call because the one specifies the actual node you're calling it from. So you need to count like the 3 node of every 3 you're calling, but since the 3 is recursive, yeah, you get the point. The thing with binary tree questions, right? Since binary tree itself is a recursive structure, there's no other way to at least nicely iterate through the entire tree if you don't do it recursively. Because like, at least if you're working with a list, this is technically a recursive data structure because it self-references itself in its own definition. Because if you've noticed, the definition of node t basically has a node t pointer. But you still can at least traverse this iteratively because it's going in like one direction. So there's only one direction to go to. But there's nothing stopping you from traversing this recursively actually, but I just find that the iterative case is easier to understand. But in the case of a binary tree, it's not, I'm not sure if it's like impossible or not, I can't say for sure, but I'm willing to say that it's almost impossible to traverse the entire tree effectively if you're doing it iteratively, because a tree has 2 subtrees, and those 2 subtrees have even more subtrees, which is the very definition of what a recursive data structure and recursive functions usually do. Like, I think you can go iteratively if you like. Let's say you explore this branch first, and then you somehow break into this branch, and then once you're done, you explore this branch, and then you break into the other branches. But doing it, exploring binary trees recursively is probably the easiest way to go. So I don't recommend trying to do it iteratively if it's even possible at all. Because of that, yeah, basically all binary tree questions are recursive if you've asked to like write code about it. Function pointers. They're basically, how should I explain this? That's a pretty, I wouldn't call it an advanced topic. But that's a pretty high level topic that I don't think you'll be expected to use in foundations algorithms. But basically, if you're declaring the tree like this, you've noticed that like the data itself is void. Void is like, if you've done JavaScript before, it's like the any data type. So C doesn't really care what data type it is. It can be anything. And to compare these void data types, you can't exactly use like less than or more than, like you can do with integers. So you have to include a function pointer to a comparison function. Because with this function pointer, your tree becomes like traversable, because if C doesn't know how to compare void pointers, it won't know how to like insert things because it doesn't know what is less than and what's more than and stuff like that. So this function pointer is simply because you're using void pointers as a data type. If you were using an int, say, like this wasn't a void but an int, you don't need function pointers per se, because int can be compared by like the operators less than, more than, equals to, and stuff. But if you're doing, and if your tree object is anything other than an int or like a string, then you need a function pointer to actually traverse the tree, because the traversal of binary trees are very, very dependent on the comparison of like 2-3 elements. I'll show you an example of like a really, really complicated tree with lots of function pointers afterwards. But yeah, to make the tree truly polymorphic, as Alistair says, which basically means that it accepts all data types, you need function pointers to compare 2 nodes in a tree. Okay, because we're running out of No, we're not running out of time. We're already going over time, but that's fine. I'm going to move on to the last question first, and you can like throw me all the questions you have afterwards. The last question is pretty straightforward though, so this should be pretty quick. So you're given like these functions, which is a recursive tree function, and then you're asked to determine what it actually does. So if you read like the functions carefully, and if you've analyzed the pattern the previous question, there's a recursive function that calls itself, which is here, and there's like a interface function that the programmer usually uses to access the recursive function. I've annotated like this recursive functions on the right side, so I'll direct your attention here. But this is very, very similar to like what you do when you write a recursive function, just that you have to read someone else's recursive function. So first you look to the base case. The base case is when it reaches a dead end, which is because it's a leaf node or like it has no subtrees. And then it just returns D, where D is the tree's data passed through like into the function. If it's not a dead end, so if there's like subtrees, it'll return the result of this function call specifically on the left subtree. And its data, like the current node's data. And this assert thing is very, very standard in all of Alistair's code, and you should be putting it throughout your code too when you're writing like C code with pointers, because it's good practice to do so before anything weird happens and you spend a few days debugging code. This function basically calls the recursive function on the tree's root if it's not null. So if the tree's root is null, if the tree is empty, if there's like no left subtree or right subtree, just returns null. But if it's not null, it calls the recursive function on the root's left subtree and the root's data. So if you convert like this to math notation, if any of you, I'm pretty sure people have at least taken like calculus 2 or something. The recursive function has two cases. If it reaches a dead end, it returns the current data. And if it doesn't reach a dead end, it calls it calls itself on the left node. And this is not accurate. It should be on the current node's data. And the function, when called on an empty tree, returns a null. And otherwise, it'll basically call the recursive function on the tree's left node. And if you combine these two together, the definition, if the tree is empty, it's going to return null. Otherwise, it's going to keep on going left, left, left until it hits a dead end, and then it returns the data. So if you call func on gin, it's going to go to bourbon, and then bourbon's going to call recursive func on beer. Beer's going to try to call recursive func on like its left subtree, but there's nothing. So it just returns the value of beer, and then it goes back up the stack until you reach the very first function call, and it returns the result of that. So these two functions return the leftmost node's data in a tree. We've gone really over time, so I'm happy to like stay back. But at the moment, I'll ask you guys to go back to the main room so I can like coordinate with the other tutors on what we're gonna do. No, since we're gonna wait on people, if anyone wants to ask any questions, feel free. I'll answer them to the best of my abilities, but I have to warn you that I am pretty rusty with the topics that is taught in algorithms, so probably won't be able to answer like KMP or BMH questions.
So for like binary tree questions,
Mhm.
do most of them always have like two functions, I guess, like one for the tree?
Yeah,
like
and
the
one
tree
to
itself, and
recurse
then
to the tree's nodes. Mhm.
okay. Because like I was having trouble before because I was like I tried to implement like the stick question, but then I didn't know what to do with just the tree itself because you need to go to like the individual nodes. So like you can't do it like with one function, I guess, right?
Yeah, the usual setup for tree functions is there's always going to be one function that calls it on the tree itself. And there's going to
Okay.
be a recursive function that is calls it on the tree's nodes.
Yeah.
Yeah.
Okay.
Oh, and if anyone wants like the notes that I've written to explain the exam questions, I can give you my notes, but I can't give you the exam questions. So yeah. If anyone's interested in that, I'll probably ask Andrew to post it into the GitHub repo or the Facebook page or something like that. Printing data in a binary tree. That do you mean to print it as an actual tree or just print it in order? Oh, if it's in order, you can basically make an in-order traversal function, but you print every time it calls the function. Does Alistair have an in-order traversal function?
There's a traversal function, but like there's no like it says like action function with it.
Oh yeah, that's wait. Let me have a look real quick. That might be in order. No, because there's three ways to like traverse a tree. There's pre-order traversal, there is in-order traversal, and there's post-order traversal. And each of them basically differs in one line, but they're used for different things. So if you want to print the entire binary tree in order, you just have to make an in-order traversal function that prints every time it like gets called. I'm assuming you can pass like a printing function into Alistair's action function, and it should print the entire tree out for you.
Yeah, I know, but like I'm just having trouble with like the making the printing function. I don't know why it's not like it compiles but doesn't work. I'm just checking my data.
Yeah, Alistair's thing accepts a function pointer, does it not?
Yeah.
Yeah, okay. I can show you that function pointer example now. Gonna get pretty whack though. I'll share my screen. So basically, I'm like second year right now. I took not computer systems, algorithms and data structures, which is the alternative to design of algorithms. But if you look at, basically, I made a tree. It's a KD tree, so it goes like to whatever dimension you want it to go, and it's also polymorphic, so it has like void pointers everywhere. But if I can find the tree definition thing, wait, where was it? It's not COMP10002, it's COMP10002 assignments. Oh, this is also assignment code, so please don't copy it. Then I don't want to get struck by plagiarism strikes. But yeah, if you want to make a fully polymorphic tree, you need like lots of function pointers. And the way you pass it into them is basically, let's say you make a pointer, you make a function. Since I'll just take one example. My key dim comparison returns an int and takes 2 void pointers and 2 integers. So you make a function that follows like this, whatever you call it, signature. So int key dim comparison. And then you basically pass this function to the tree call. So when you're calling make empty tree, you can do that. Then you pass in like some dimension, and then you pass in this function. But you pass in the pointer to this function, which is very important. So you dereference the function like it's a variable, but it's actually a function. So you return the pointer to the function. It's a bit weird. It's kind of an advanced topic, but it's very, very useful in like the more advanced classes that you take after foundations of algorithms. If I can take Alistair's tree stuff for a bit. Well, the copy paste didn't work. The one that is action is basically this one. I think this this 3 things implies that this recursive whatever you call again function is an in-order traversal of a tree. And since you need to pass in like a void pointer into a function pointer into here, so I'm just gonna copy these into like a new file. Then I'll write example code on how you would print the contents of the tree. So yep, if you want to like, let's assume that like the void pointer is a pointer to an int. It's just not defined like that because polymorphic trees, you know. So if you, let's say, want to make print data, and then you take a void pointer, then you dereference this to an int, say yeah, that function should print the data, assuming that you've casted it properly. And then if you want to like call the traverse tree to print the data, because the traverse tree function traverses in order, you can do something like traverse tree. And then I'm just gonna pretend that the variable tree is an actual tree. So I'll just pass it like that. And you call print data like that. That's how you would make a printing function, which is basically this. And then you feed the function pointer of the printing function into Alistair's traverse tree function, so that this function is run on every single roots data. every single node's data. But like, don't worry too much about void pointers at the moment, because I don't think you'll be expected to use it in the exams. It's just a good to know, because if you want to make your data structures polymorphic in the future, you're pretty much forced to use a void pointer. And like when it's polymorphic, when everything is in void pointers, there's also like things that you have to add, like comparison function pointers and stuff, to make your tree work properly. Because you can no longer hard code the comparison function inside your trees, like let's say traversal function or inserting function, because you don't know the type of data that it will be. That's why you need a comparison function.
So are you doing design of algorithms?
No, I did algorithms and data structures last semester, because I'm at a mid-year intake and DOA is only available for like semester 1.
Is that easier?
Yeah, it is somewhat easier, at least from what I've heard from my friends taking DOA. But I sure as hell didn't make it easy for myself, because if you look at my ADS code, even my friends in DOA say it's insane. So yeah, just look at my tree definitions, man. Makes me want to die sometimes. Like, you see the amount of function pointers I have to pass into a tree to make a tree actually work.
True.
Yeah, this is like a 300. No, this is the header file. It's 100. Like, yeah, it's just void pointers and function pointers absolutely everywhere.
Oh man.
Pretty disgusting if you ask me. Not gonna. My tutor even asked when I did this, but why? And I said, I'm kind of bored, not gonna lie. But yeah, that's just how it is. Like, you can always make life very, very hard for you in assignments. I don't recommend that, but if you have nothing to do, might as well. Basically, if you basically the tree thing I showed you, this is also built on Alistair's tree, just expanded to crazy levels. Because if you look at my attributions, this is like a code review now, not exactly a tutorial. But if you look at my attributions, it is derived from like the thing that you're learning right now. So just taken to the extremes, which I'm not sure exactly why, other than boredom. But don't do what I do and be a sane person, I guess. Because I also took Alistair's list code to the extreme. Not quite extreme, but like at least there's no function pointers here. But the thing that I did, which is insert in order, which is exactly what we did in the breakout room just now, SE1 question 4 part A. I just wrote this without knowing that that sample exam exists, so it took me a few days. And my implementation should be a bit more efficient than what was implemented in the exam answer that I showed you just now, because it first checks if like the new item is the head or the tail. If it does, it just puts it in and skips it, instead of like looking through each element one by one. Only difference being that the one that Alistair showed, Alistair's code is basically a singly linked list. So one node only has links to the next node. It doesn't have links to the previous node. I modified it such that each node has a link to its previous and next node. So it's easy to like go back and forth throughout the list.
Okay, I see.
And if you've noticed, this thing also has function pointers, because the data is a void pointer. Very, very similar to Alistair's list, because there's Alistair's tree, sorry, because there's a comparison function, and the other thing is just a print function to make life easy. But yeah, void pointers are nice, but you have to like be very, very careful, because once you use void pointers, C won't warn you regarding any other pointer stuffs. and you need like additional auxiliary functions to make everything work nicely. So do I recommend using it at this stage in time? No, but will you need to use it later on? Yes. Probably like if you take DOA, I think it's almost guaranteed you're gonna have to use a void pointer somewhere at some point in time. Oh, but I can like post this code snippet too if you want. I'll ask Andrew to post it somewhere on how to use Alistair's traverse tree with a void, like with a function pointer. I'll just like add some comments.
Oh, seems like everyone left.
Yeah, nice. Yeah, it's not supposed to stretch out till 6:30 anyways, because like the allocated time was, I don't know, 4:30 to 6. We're going like 30 minutes over time, but I'm happy to stay back for questions. According to the, what do you call that?
So are you doing computer systems or like data science?
Yeah, I'm doing computer systems and software modeling and design at like this semester.
Okay.
The list code I just showed you just now, that was from like literally my first computer systems assignment.
I'm doing data science anyway, so it's okay. I don't have to.
Oh yeah, should be fine. You don't have to like go to that lengths of C mastery.
Yes.
It's like, trust me, after doing C for 3 semesters, you get sick of the language.
I prefer Python. It's a lot easier to use.
Yeah, that's why.
So much work.
Yeah, it's gotten so bad to the point that right now I can't use Python because I'm so used to like using C. That's like really, really bad. Traverse example. Yep, I'll make sure to like ask Andrew to post that. Any other questions?
Nah, I think it's good.
Yeah, no worries. I'm actually gonna check if like people are still in the breakout rooms or not. Oh, the sign before the print data thing. That sees the reference pointer. If you want to dereference a pointer, you have to use the and like thing. Yeah, ampersand.
I just get confused when it's like when someone says dereferencing or like ref like.
Oh wait, actually no. That's my bad. And isn't dereferencing. And is actually getting the pointer too. So it's what's that? What's the opposite of dereferencing? Dereferencing uses the star, right?
Yeah.
If you want to dereference a pointer, you do the star pointer. Getting and is getting the address to whatever.
Yeah.
So when you're doing the and functioning, you're getting the address to that function, which is basically a function pointer.
Okay, I see. Yeah, because I was kind of confused because like I thought dereferencing was using the star.
Yeah, my bad.
Getting the value.
When you get used to like dealing with Python, it's just intuitive for you. Then when you try to explain it to somewhere else, you're like, what? Yeah. It's pretty rough once you learn lots of C. Wait, is nobody literally in this breakout room anymore?
No.
That's kind of, wait, seriously though. That's kind of sad. Wait, is the breakout room still open? Oh, there are still some people around.
Well, let me see if there's any questions.
Yeah, there's still some people in room 5. If you want to move there, I'll move there too. Can you move rooms by your own volition, or do I have to assign you to a room?
I'm not sure. I think you have to assign me probably.
Oh, cool. I'll move you to room 5 if you want to ask Andrew some questions. I'll go there after you.
Okay.
There's like people with questions, so I can answer them. Yep, you can join room 5 now. Just click breakout rooms on the bottom. Yep.